Yes, welcome once again, members. In this lesson, we're going to be looking basically at the force of gravity and weight. I know that you've looked at mass already, so shall a short brief about mass and then look at the force of gravity and weight. So, by the end of this lesson, you should be able to define what weight is, state its SI unit, calculate the weight, and then give reasons as to why the weight of a body varies from place to place, and to give the relationship between all the differences, differentiate between mass and weight. So let's begin by looking at mass quickly. I need you to get a piece of paper and pen and write down any 4 or 5 things, any 4 things that you know about mass. Okay, so number one, I will know that mass by definition is defined as the amount of matter in an object. It is the quantity, it is the amount of matter in an object. We know that its SI unit is a kilogram. We know that the mass of an object is the same at any place. In other words, it is a constant. Mass is a scalar quantity, and also it is a basic or fundamental. We know that it is a basic or a fundamental quantity. That is what we know about mass. And of course, it is measured by using a beam balance. It is measured by using a beam balance. So, how about weight? What is weight? So when you come to weight, we're going to begin by looking at an activity. So get your pen and throw it up into the air. Yes, what have you observed? Yes, the object has moved up and then it has changed direction and then it has fallen down again. When we look at the rain simply falls to the ground. It doesn't go up into the heavens. It simply falls onto the ground. In other words, any object that has mass, anything with mass, that object is always attracted towards the ground, towards the earth, in case we're on earth, towards the moon, in case we're on the moon, towards Jupiter, in case we're on Jupiter, or on any other planet. Each planet has its own force of gravity. So, in other words, we define weight as the force of gravity on an object. It is the force of gravity on an object. Or we can simply define it as the force exerted by one body onto another that freely supports it. But in short, you can simply say that it is the force of gravity on an object. Why the force of gravity? Is because each planet has its own force of gravity. So, meaning that all objects on a given planet which are attracted towards that planet will give us a force which we call the weight, which we talked about earlier on. So, another thing that we need to know is not that weight is a force, and therefore it is measured in newtons. It is also, we need to note that on the Earth's on the Earth, the value of G is equal to 10 meters per second squared. I'm going to talk about this one later on, but we need to note that if a body on Earth weighs 10 newtons, then on the moon it will weigh a 1/6 of that on the Earth. We shall look at this in detail shortly. Weight is measured by using a spring balance. We talked about that as well. And the spring balance looks like that. It is taking measurements from the spring balance. Another thing that you need to note is that weight is a vector quantity. In other words, it has a size, that is the number, 2 newtons, 3 newtons, like that. And then it has a direction. It is always acting towards the ground, towards the earth. Another thing that you need to note is that weight is also a derived physical quantity. A derived physical quantity. We say that mass is a fundamental quantity. So we have two things. We have one, weight is the definition, force of gravity on an object. 2, it is measured in newtons. 3, it is a vector quantity. 4, it is a derived physical quantity. And then 5, it is measured by using a spring balance or a Newton meter. Measured by using a Newton meter or a spring balance. Whenever we're going to talk about weight, there's what we call the acceleration due to gravity. In the previous sections, we talked about accelerating somewhere. Do you remember what it is to accelerate? Yes, it means to speed up, to increase on the speed. We shall look at acceleration details when looking at motion. The acceleration due to gravity on the Earth goes on changing. The acceleration due to gravity goes on changing from place to place, from planet to planet. In the case of at sea level, it is different from when you're from the top of the mountain. So it keeps on changing from place to place. Basically, two reasons as to why the gravity, force of acceleration of gravity keeps on changing. So the reason as to why the acceleration due to gravity changes from place to place, from planet to planet, or the reason as to why the weight of the body changes from place to place, because remember that weight is equal to mass times the acceleration to gravity. So if the acceleration to gravity changes, then automatically the weight must change. But remember that mass is a constant because it is simply the quantum of matter in an object. The mass doesn't change. So the reason as to why the weight or the acceleration to gravity changes from place to place is simply because of different reasons. Is that number one, the Earth is not a perfect sphere. The Earth is not a perfect sphere. In other words, there's a different height at a different point of the Earth. For example, the sea level and the top of the mountains are at different heights from the center of the Earth. And therefore, because of that difference, the weight or the acceleration of gravity changes. Another reason could be the spinning of the Earth as it is moving around the sun. The Earth is always spinning. That's why we have the day and night. So that spinning also has an effect on the value of the acceleration of gravity at any point. As you move away from the sun going to other planets, since we're moving from the center of the Milky Way galaxy, we shall talk about this later on, as the distance changes, even the acceleration of gravity changes. So likewise, it also changes like that. And the weight of the body or the weight is very important in especially keeping the air around the Earth. You know that air is very important. The oxygen, nitrogen, carbon dioxide, and so on. All those gases are very important to us. So the weight of the body is important in keeping those gases nearer to the ground. At the moment, we need to know that on the Earth's surface, the acceleration to gravity g, it is always represented using eta g. It is always equal to 10 meters per second squared. Now, as a person who's doing physics, as a person who's a scientist, you must know this, that g on the Earth's surface is always equal to 10. Then, for the other planets, they can always be given to you at any time. Of course, when it comes to A level, we shall be more precise, more accurate, and the value of g will be equal to 9.81. But at the moment, let's take it to be 10. In other words, round off. On the moon, it is a 60th, 1/6 of that on the moon. In other words, it is 10 out of 6, 1.6667. On Mars, it is 3.7, on Jupiter, 24, Pluto, 0.7, and the Sun, it is 270 meters per second squared. So, at the moment, don't forget this, that on Earth, G is equal to 10 meters per second. So, how do we calculate weight? Weight of a body is given by a formula, mass times the acceleration due to gravity. In other words, weight is equal to m times g, whereby the mass must be in kilograms. If you've been given the mass in grams, then you must convert it to kilograms. In case you missed this, please go back and look at how to convert mass units. And its SI unit is a Newton. The mass must be in kilograms, and the acceleration must be in meters per second squared. So, we also need to know that on the Earth's surface, a mass of 1 kilogram has a weight of 10 newtons. How does this come up? It is simply coming from the formula W is equal to mg. And this is the same as the mass is 1 kilogram times g, which is equal to 10, always on Earth. The answer is 10 newtons. So we have this question here which says that calculate the weight of a body whose mass is part F 5 kilograms. You can pause the video and write out all these questions before we discuss them. So we know that weight is given by m times g, where m must be in kilograms. So our m is 5, our g is 10 on Earth always. So this gives us 15 newtons as the answer. For part B, we do the same. We shall simply say that weight is equal to mg, which is the same as the mass is 100, the g is 10, the answer is 1000 newtons. For this one, you first convert it to kilograms. You remember that King Henry's daughter Mary drank cold milk. So from kilo, hecto, deca, then the m, where the m is, we shall simply put there the g to mean the mass in grams, like that. So 1 kilogram is equal to 1000 grams, meaning that 1000 grams is equal to 1 kilogram. How about 1 gram to be the same as 1 over 1000 grams? How about 500 grams? It is the same as 1 over 1000 times 500, which will give us 0.5 kilograms. So in other words, this is the same as 0.5 kilograms. So weight is equal to m times g. The weight is 0.5, the mass, the g is 10, the answer is 5 newtons. Hope that you got that one right. Likewise, weight is equal to m times g. The mass is 40,000 milligrams, and what is this one in kilograms? It will be 0.04 kilograms. 0.04 kilograms. So we have 0.04 times 10, which gives us 0.4 newtons. Then 3.5 tons. This is the same as 3.5 times 1000 kilograms. So this is the same as 3500 kilograms, meaning therefore that our weight is equal to m times g. The mass is 3500 times 10, which gives us 35000 newtons as the answer. So that is what we do. So I'm leaving you with an activity which says that give 5 differences between mass and weight. Use the definition, use the units, use the instruments to measure them. Are they scalar vectors? Are they fundamental, basic? Use any of them. You can use a table and give differences between mass and weight of the body. So at the moment I'm stopping here. Let's meet in the next chapter, the next part.